Welcome to the Unit 3, Session 6 of our Financial Modeling course. In the Session 6 of the Unit 3 of this course, we are going to consider diagnostics on the error term. We have earlier considered the diagnostics on the explanatory variables or the regressor or the regressors. In this session, we are considering the diagnostics on the error term, which is also one component of our financial modeling or our model. By the end of this session, you should be able to explain the meaning of heteroscedasticity as it applies in regression model and also understand the effect of heteroscedasticity on the regression result. It is important or imperative to understand that one of the main assumptions of the classical linear regression model is that the errors or the error term have a constant variance. So the variations in the error term or the errors within the model or within our model is constant. So there is a constant variations in our error term, the term that we discuss as homoscedasticity. So the absence of homoscedasticity, or if we model and we test and realize that there is no, the variations in the error term is not constant, or there are disparity among the variations in this error term, then we are no longer considering homoscedasticity, because homo means equal and scedasticity means variance. So homoscedasticity simply means equal variance. But with the hetero, we are simply saying that the absence of homo, so meaning unequal, hetero means unequal, so homoscedasticity deals with the presence or constant variance. But if we find ourselves in a situation where we have unequal variance, then the issue of heteroscedasticity comes to play. So heteroscedasticity is always a problem, or is an issue that occurs among cross-sectional data. It will hardly affect time series, because time series data always deals with issues like autocorrelation or serial correlation. But with homoscedasticity and heteroscedasticity, there are issues that occurs among cross-sectional data. The causes may be that there is the presence of outliers. By outliers, we are simply saying that there are data sets or the data points find themselves far off from the center. So they are, if you plot them, you are likely to find some portion of the data set being far off the center. So some are at the extreme ends. Or it could also be caused by incorrect functional form of the regression model. So if you fail to add the appropriate parameters or variables in your regression model, you are likely to also come across the issue of heteroscedasticity. There is also incorrect transformation of data. So in the transformation of your data, assuming you transform the data with the wrong set of transformation or with the wrong transformation technique, you are likely to also face the issue of heteroscedasticity. Or finally, there is also the idea of mixing observation with different measures of scale. So here we are simply saying that there are generally four scale that we use in regression analysis, assuming, which we earlier said, that they are the nominal, the ordinal, the interval, and the ratio. Mostly we said that in regression analysis, the dependent variable should always be in either interval or ratio form. So assuming you mix the categorical, or what we call the nominal and the ordinal data with the ratio and interval data, there's also the chance that you're going to face the issue of heteroscedasticity. So we have to be careful in terms of regression, or when we are modeling or estimating our models with some of these variables. The consequence of this heteroscedasticity also includes that the coefficient estimate will no longer become unbiased, or they are no longer unbiased, but they are no longer best unbiased, because we said that the regression analysis should be blue, which is the best linear unbiased estimate. But here we are saying that we are likely to face the issue of unbiased and consistent. So the data will be unbiased and consistent, but they are no longer going to be the best linear unbiased estimate. So means the presence of heteroscedasticity makes the data set, or makes our model only linear and unbiased, but not best linear unbiased. Finally, there is also the chance that our T and F statistics or test will become unreliable. So we are likely to face the issue of unreliability with respect to our test statistics. And these are all problems that we have to deal with when we are estimating our models. So this is the heteroscedasticity plot. So before we do a formal test for the heteroscedasticity, that is, we test using the Bruce-Pergen test, it's appropriate to plot the residuals to provide an insight or overview as to how the plot or how the residuals look like graphically. So figure 3.2 is a residual plot which is meant to detect heteroscedasticity among the data set or the return or class series. So this is our y axis and this is our x axis. You could see that this is a straight line which method or which has separated the variables into the lower and the upper part. You will see that as these variables move along, there is the idea of, or there is we observe, or we can witness an expansion into how these plots are moving. So if you plot the residuals of an equation with respect to the potential z, this z, so these variables, so the residuals, and you realize that the z proportionality factor is expanding, it simply indicates the possible, or it's a simple indication of the presence of heteroscedasticity, because as you see, as these plots move along the straight line, you could clearly see that they are expanding. The points are expanding as they move along this straight line, which indicate that there is the possibility of heteroscedasticity. Figure 3.2 is a squared residual plot for detecting heteroscedasticity. So unlike the previous last figure, that's figure 3.1, which was the absolute residual, here we have squared the residuals, and you can clearly see that there is also a pattern. They are following a pattern. We are fitting our residuals against the actual values, and we are trying to detect the presence of heteroscedasticity. But the best means of detecting heteroscedasticity will not be visually, or we cannot always estimate, or we cannot be perfect, or we cannot be correct in estimating in diagnosing the presence of heteroscedasticity using plot, as there are formal tests that are used in detecting the presence of heteroscedasticity among the error term, or the variations in the error term. So below is the procedure that we have to pass through in plotting the heteroscedasticity plot that we saw in our previous slide. So here we are using eViews application. So it is imperative, or it is important that you download and install this application so that you can also use, or you can test some of these diagnostics with the help of the eViews application, or you can also make good use of these simple illustrations. So in your model view, you will select the proc. This will be in the model view, and then in that dialog box you make residuals of your series. Here it is also advisable that before you even do this, you already have loaded your dataset in the eViews application, and you have estimated your regression analysis. So there's a chance that you have your residuals in there after all this process. So after you have done so, you rename this as receipt CR, because you don't want it to conflict with the other data that you have saved in the eViews application. So after you have done so, you click OK. So this is for the first plot that we saw, because it was for the absolute residuals. But for the second plot that has to do with the squared residuals, you have to square the same receipt CR. So for fidget values in that model view, you wish to forecast and rename this as fitted CR. So we have estimated our residual CR, then we have squared the residuals and save it as receipt CR squared, and we have the fitted CR also, which is at the forecast, and we rename. So if you want to plot this heteroscedasticity plot, you only have to open this saved data set, which is the fitted CR and the squared residual, even the receipt CR, and among these values you can plot it with the help of the eViews application. So as you have, it is the most important thing that you should have your data saved in this form, and then you can plot them using the eViews application. So we are saying that the BP test, which is the Bruch-Springen test, is used in testing for the presence of heteroscedasticity, that is formally. So with this test, using our eViews application, we have to pass through this process in estimating the Bruch-Springen test. So in our eViews application, the first thing we have to consider is that before we even think of estimating the Bruch-Springen test for heteroscedasticity, it should be It's a condition that we have already calculated or estimated our regression model. Therefore, we are going to test this, the presence of heteroscedasticity within this already estimated model. So here we estimate the OLS regression, and we obtain the squared OLS residual from this regression, as we have done already in our previous session, where we had table 3.1, 3.2, and 3.3. So we estimate the OLS regression and obtain the squared OLS residual from this regression, as we have already done. So the next thing is that we have to regress the square residuals on the last term or the last regressor term, which we include in the model. And then we have to state the null hypothesis, which in this case is that the error in the variance is homoscedastic. So it means the error is there are equal variance in the error term or the residuals. So this is homoscedastic, so it means equal. So the null hypothesis is that the error in the variations in the error term is equal. So all the slope coefficients are simultaneously equal to 0. So there are no variations, or the variations are constant. So then we use the F statistics from this our regression analysis after testing for the Bruch-Pergen test as a means for evaluating the significance or otherwise of our results. Table 3.11 is the result of our Bruch-Pergen test, which we tested on our previous regression model for the estimation on the credit ratings of the customers of a bank. So you could see that we have the descriptive as usual. So our test is the test of heteroscedasticity, which is Bruch-Pergen test, and we have our F statistics, which are very important, and the R square, which is also important, together with the chi-square. So this is the chi-square result, and this is the probability for chi-square there. So we are using the F statistic and the R square. The alternative is the use of the R square, and you can use the F statistics to determine whether we have to reject or we fail to reject the null hypothesis. The other factors are important, but we have already seen them, so we're not going to focus on them. So you can see that from this table we have a coefficient or result of 14.92495 and a probability value of 0.0000, meaning we don't have enough evidence to prove the absence of heteroscedasticity or the presence of homoscedasticity among the data set. So with this value, we can clearly claim that we have to reject the null hypothesis of homoscedasticity, means there is the presence of heteroscedasticity among among our model or within the model set. The alternative way is also to use the chi-square. This is the chi-square result, which is the R square, which is the same as the chi-square result, and it also has a probability value of 0.000, indicating that we don't have enough to conclude that there is homoscedasticity. So we have to reject the null hypothesis in both tests or in both results. So you could see that we have both the F statistic and also the chi-square or the R squared coefficient, which is being tested using the chi-square value. So here, assuming we have a significance level of 5%, the idea is that we have not been able to meet this value because we have 0.00, which is less than 0.05. So we should have a value more or equal to or more than 0.05 for us to confirm that there is homoscedasticity within these values or within this model set. So from the previous slide, we made the conclusion that there is the presence of heteroscedasticity among the error term or the residuals. So the variations in the error term in summary are not constant. So under this session, we have learned that the error term diagnostic is an important tool in regression analysis, as we earlier estimated using the plot as well as also the format, which is the Bruch-Pergen test. We came to realize the relevance of the heteroscedasticity test. The problem of heteroscedasticity was also established, and we came to realize that it leads in the unreliable estimation of both our T and the F test. So in summary, we have discussed the diagnostics on the error term, and we have come to the conclusion that the estimations of our credit ratings would had or exhibited difference of heteroscedasticity. So we are going to continue with the unit 4 of this session in the next session. Thank you for your valued attention as we meet the end of today's discussion. Hope to meet you once again in our next session. Thank you and stay blessed.